Okay, let's continue. So this is the second lecture. And we're going to see two things. Well, maybe I should not write it. First is a version of the Mermin-Wagner theorem for correlation function with a very nice proof, which Fröhlich showed me recently. And it's really kind of simple, straightforward. And for anybody who has already tried to see a proof of Mermin-Wagner, it's full of commutation relations, Fourier operators, and it's also kind of limited application. Here you should be convinced that it's really nice. And then we'll get a proof of, an introduction to reflection positivity and infrared bounds in the context of a classical Heisenberg model. So I'll see what I can do in just an hour. Sorry, it's... So first, Mermin-Wagner theorem. Let me give you a brief history for this. So the first paper, I completely forgot what I was supposed to ask. To wait for the indication. I suppose I continue. Okay. So first paper was in 1966. This is the paper of Mermin and Wagner, who proved indeed the absence of spontaneous magnetization in 2D Heisenberg model. The quantum version, it's a curious story, but the proof for the quantum system turns out to be simpler than for the classical one, at least initially. And it was first done by Mermin and Wagner for the quantum system. 1971, there is a paper Fischer just now or Yasnov, I'm not quite sure. And this is the first paper on an explicit bound on the decay of the two-point function. The bound was not very good. It was decaying like 1 over logarithm of the distance. Actually, even not that, it was 1 over the square root of a logarithm. So extremely slow decay, but still it was an explicit bound for decay of two-point function. And this was using Bogoliubov inequality and Fourier transform. Then in 1977, there is a beautiful, extremely short paper of McBrien and Spencer. I think the paper is 4 pages in Communications. And even because they do a bit extra things, 2 pages would have been enough. And this is really a case where they find kind of a simple, complex analysis way of understanding the classical Heisenberg model, and they extract algebraic decay, not 1 over the square root of logarithm, but really 1 over the distance to some power. So this was really it's a fundamental paper also of statistical mechanics, extremely short, and they introduced the so-called method of complex rotation, which applies also to quantum systems, as we'll see. And in 1992, also another beautiful paper of Koma and Tasaki, who prove algebraic decay for two-point function in the quantum Hubbard model. But the method definitely applies with no change to the quantum Heisenberg model. The proof here is going to be even simpler than Koma-Tasaki. And it's somehow inspired by McBrien Spencer, but somehow, certainly there are complex rotations, but for the rest it's really quite it's technically a bit different. And I apologize for writing again too small. I have to remember writing bigger. So then I need a little bit of technical, there is a technical equation which nobody is going to appreciate. So decay is measured by the following function. So it's going to be measured by exponential of minus a function I'm going to write xi, depends on beta, it's important, of x. This is going to be a bound for the correlation function between the site 0, the origin, and the site x. And what is xi? We would like it to be as large as possible. And here it is. And it works for any graph. Xi beta of x is going to be the sup over fields phi y, which belongs to R of lambda. So at each site you get a complex angle. Phi it turns out to be a real number, such that phi 0 equals 0. And then you take phi 0 minus 2 beta s square, the sum over nearest neighbors in E. And then you take essentially phi y minus phi z to the square, but unfortunately it cannot be just as simple. So it's going to be cosh of phi y minus phi z minus 1. And right, I should close all those things. So the thing is that the soup is going to be the largest number you can put at phi 0. Yeah, maybe a picture is really necessary for understanding this. So it's going to apply really to two-dimensional systems. You have a lattice, you have a 0 somewhere, you have an x somewhere else. And now you're going to try to find the, sorry. Yes. Oh, no, sorry, it's something silly, isn't it? No, forget this. It just cannot be. I guess it's phi x. No, forget this, I got it wrong. Like that. So the thing is that you try to maximize the value of phi at 0, and then you, it's phi x, sorry, phi x has to be 0. That's the thing. So, yeah, put the condition, otherwise it can be quite large. Just take a constant phi huge, and it's going to give you plus infinity, and it's a bit too good. So here you must have 0. Here you try to get as much as you can, and in order to get as much as you can, well, the price you pay is that you're going to sum essentially the difference to the square. So when you minimize this, you get something like a harmonic equation, discrete harmonic equation. And you know that in 2 dimensions, you can get logarithmic divergence when you fix the boundaries. Yes? Oh, it's, sorry, it's the sum of yz. Yeah, here, phi x equals 0, and thank you. And we sum over pairs yz. And this is phi 0 indeed. So let me just, so exercise. And this is an exercise in the notes, but I give you an explicit function phi to use. And you can check that psi beta of x works like, I mean, is of order 1 over beta, the logarithm of the distance between 0 and x. You can reach something like that. And then it means that when you take exponential minus this, you get indeed the distance to the power constant over beta. I give the beta because it's good to see that the algebraic decay gets less and less decay as beta goes to infinity. So what is the theorem? So I mean, yeah, this is the annoying part of the proof. One has still to work out some decay out of this thing. But if you agree that you can get some decay out of that, the theorem looks nice, and the proof also, which is that if you take the 2-point function between 0 and x of any spin direction at h equals 0, then this is bounded below, I mean bounded above by, well, comes a constant 2s squared. It's not very important. Exponential minus this psi, beta of x. So this is an explicit upper bound for the 2-point function, and the psi beta can be made to diverge with x in 2 dimensions or less. So the proof so this is a method of complex rotations, and it uses I mean, we are going to use Schrotter product formula, and the Hölder inequality for traces. So this play an important role. I'm going to change the notation also. And here it's more convenient to consider the usual XY model. So H is going to be -2, the sum of nearest neighbors, and Sx1, Sy1, plus Sx2, Sy2, plus U, Sx3, Sy3. So it's of course equivalent, but it turns out that here it's convenient to imagine that the continuous symmetry will definitely be in the 1-2 plane, and possibly also in other planes, but we actually only use continuous symmetry in one plane. And then we use the S plus and minus operators. I'm going to use let S plus and S minus at site y to be like S1 at site y plus or minus I Sy of 2. So I suppose you know that those operators are useful. And we can use that the effect of rotations on those operators. So what is useful to know is that if you apply exponential of A Sy3, and then add to Sy plus or minus, exponential minus A Sy3. So I have written down at some point the equation for where, at least when A is purely imaginary. It turns out that by basic complex analysis, it applies to also real parameters A. And this gives you exponential plus or minus A of Sy plus or minus. So this is something which turns out to be true. And this is true for every A in C. We are going to use it for A in R. And when you have A to be purely imaginary, this corresponds to usual rotations. So hence the name of complex rotations. So then one can rewrite the Hamiltonian using those operators, and we get that the Hamiltonian is minus the sum and xy in the set of edges. And then we have S plus x, S minus y, plus Sx minus, Sy plus 2 U Sx Sy of 3. So it really helps to work with those operators. Next, we defined what plays the role of unitary operator on rotations, but it's not unitary anymore for complex rotations. We take the product over y's in lambda, exponential phi y Sy3. So we are given some numbers phi y, so a number for every site, and we construct this operator over here. And so where each phi y belongs to R this time. And we apply this to the 2-point function. So there is something I'm not going to do, which is that we are interested in the decay of this function. I'm going to look at the decay of the correlation function S plus S minus. Just expand it and check that it's equivalent to the problem here. So we look at this trace of S0 plus x minus exponential minus beta h lambda. Well, actually, let me drop the lambdas. So we would like to say that this, when divided by the partition function, I mean the trace of exponential minus beta h, is bounded by this exponential minus xi. Okay, and then this, we say that, well, this is the same as the trace of A, S plus 0, Sx minus, A minus 1, and then exponential minus beta, A, H, A minus 1. So I suppose many people are familiar with this. If not, just imagine expanding this using Taylor series. You can, we have only matrices. And then for each product, you can Sorry, you can group the AA minus using cyclicity of the trace, and they all disappear. So then we calculate how the A changes the Hamiltonian. And we have that A minus 1 is like minus the sum over YZ, or let me write XY in E. And we know how to make we use this property every time. And what we'll get is exponential phi y minus phi x. So actually, sorry, I have here really yz. And s plus y s minus z plus exponential minus phi y plus phi z s minus y s plus z and plus 2u sy as z in the direction 3. So this, of course, does not change. Then we would like to say that it does not change too much compared to the Hamiltonian h. So we can write that this is like h. And the correction has the form minus yz in the set of edges. And the first thing will be, the first thing is that, actually, let me just write down what we get. We get the cosh of phi y minus phi z minus 1, which applies to sy plus s minus z plus s minus y s plus z. It's not too hard to check this. I mean, of course, it comes from this. You subtract 1, and then you rearrange the terms using some using the fact that this is a symmetric thing. I let you check the details. This is what we get, and then we still have an anti-symmetric part, which is minus the sinh of phi y minus phi z, and s plus y sz minus s minus y sz plus. So this is what we get. We get the whole Hamiltonian, and then those terms, which are, of course, 0 when the phi's are constant. And let us write this as, understand this as h plus b plus c. So b is all those terms with the cosh minus 1, and c are all those terms over here. So the important properties to note is that b star equals b. That's quite clear because the adjoint of s plus is s minus, and conversely. And on the other hand, for c, you have you subtract s plus s minus minus s minus s plus, so it's anti-self-Hermitian. So we have that c star equals minus c. So now, so what we have is that we have found that the trace of s plus 0 sx minus exponential minus beta h is like equal to exponential phi 0 minus phi x. This comes from the first part, the a s plus 0 s minus x a minus 1 trace s0 sx plus minus, and then exponential minus beta h minus beta b minus beta c. And now we are going to bound all those terms, and the curious thing is that we can recognize the partition function there. So recall Hölder. It might not be familiar to everybody. The Hölder inequality for traces. I know it's very familiar for some. So this is the trace. Take the absolute value of a to the r to the power r, 1 over r. And then the inequality is that if you take the product of two matrices, A, B, norm R, then this is less or equals than norm of A, B, norm of B, Q, for any P, Q, R larger or equal to 1, including plus infinity, such that 1 over R equals 1 over P plus 1 over Q. So this is something interesting. By the way, the proof of Hölder's inequality for traces turns out to be very complicated, much harder than for functions. And a nice proof is due to Troelich 1978, which uses notions of reflection positivity and chessboard estimate. So it's also a good proof which fits the setting of what we are doing here. I gave it as an exercise. I don't expect anybody to be able to do it, but Stephen Tate, who is going to help for this working session, may give you the proof if there is interest. So now we have all elements to carry the proof. So using Trotter, we can write the following. Trace, so we are starting from here. S0 plus Sx minus exponential minus beta h minus beta b minus beta c. We write this as the limit n tends to infinity of the trace S0 Sx. And then we get simply all this exponential minus beta over n h, exponential minus beta over n b, exponential minus beta over n c, everything to the n. And now using, do I still have, no, I'm going to continue here. So using Hölder for this product, by the way, Hölder also applies to more than just two matrices. If you have A1, AN, and you just have that the sum of 1 over PIs be equal to 1 over R. So when you do this, you get that this is less or equal, so we use the Hölder's inequality under the limit. First, we take this thing, the norm, when R equals infinity, which means the standard operator norm. Then for those operators here, we take 1 over n. And we'll get norm of exponential minus beta n, h, n to the power n. And for the rest, we take the infinity norm. So exponential minus beta n, b, infinity to the power n. And exponential minus beta over n, c, infinity to the power n. I hope it's still possible to see. So the sum of all the 1 over pi's is obviously 1, because you just have n times 1 over n here. All the others are 1 over infinity. And then we can check the following. This is not too hard to check. It's 2s squared. This gives a prefactor over there. It's not very important. What is curious is that this turns out, I mean, since you have, you write it up explicitly, and what you get is just the trace of exponential minus beta h. So you can group all those operators, obviously, together, and that's what you get. I mean, beta over n h raised to the power n. This is what you get. So we get exactly the partition function on the right side. That's very important. And this, well, we just bound it by exponential beta b and, beta norm of b, the simplest possible bound. And here we don't need to care about this. This would be a dangerous term. If we bound it the same way, we would get the sum of the sinh of phi y minus phi z, which would be a problem. We can tolerate these things to the square, like in the cosh, but not in the sinh. But at the same time, the C is anti-Hermitian. So this is like a unitary matrix. So the infinity norm is 1. The sup norm, the operator norm. So we can forget it. And the next thing is to realize that the operator norm of B is less or equals than 4s squared, the sum of yz in the set of edges, and the cosh phi y minus phi z minus 1. And we get the result out of this. Okay? So this is exactly in the form of, I mean, you have this phi 0 minus phi x. Now you can, this works for all phi, so you can also set the phi x equals 0. And you get this exponential of, I mean, the correction in the psi. So all the second part. So then, yes, it proves it. So this is really a remarkable way to get quite easily this decay. And you might still find it a bit complicated, but please look at Ueltschi's book also to see all the versions of Mermin-Wagner theorem. And you have so many commutators to calculate that, yes, you'll settle for this proof with no hesitation. So second part, I'd like to discuss the classical Heisenberg model, unless there's a question. So the proof is quite nice, and certainly does not need a regularity of a lattice, which you should not in order to get this theorem. The theorem is really, I mean, this decay of correlation is due to the continuous symmetries of the spin. It's not due to the fact that the graph is regular. So the initial proof using Fourier analysis, they are using something which should not be necessary. Yes? If you take a layered graph, that's the question. A tree, yes, absolutely. But for a tree, you would have exponential decay of correlation no matter what. If you fix 2 points and you wonder, I mean, 2 points would be essentially like a one-dimensional system, and you should have exponential decay in all cases. So, but yes, this would apply to a tree, absolutely. Okay, so next, the classical Heisenberg model and long-range order. Okay, let me move this up. Does it work? So I'd like really to introduce the method of reflection positivity and infrared bounds. I still have 25 minutes to do that. It's going to be enough to get an idea of the proof, but certainly not to go in details. So let me write the title here. So long-range order in classical Heisenberg model. So I need to introduce the formalism, which is, of course, a bit different from the one for quantum systems. That's certainly simpler. The state space is the following. It's going to be denoted omega lambda. It's the Cartesian product over all sites x in lambda. We still have the same graph as before of S2. Right, let me not put a bar because it's unreadable. S2 of lambda. This is a notation which some people like and some have troubles with. It means the set of all functions from lambda to S2, which basically means that at every site you fix an S2 vector, a vector in 3 dimensions of unit 1, of length 1. So this is the picture we have. We have a graph, and at every site we have a little vector pointing in some directions in the unit sphere S2. And the Hamiltonian is a function on the state space, and the function of configuration sigmas, sigma underline means sigma x at every site, is going to be given by -2 the sum over xy in the set of edges, as before, sigma x times sigma y. This is the inner product in R3. Yes? No, it's the sphere. That should be the mat BBS. Maybe this is a better, that's readable notation. And so that's the Hamiltonian, and we can still put a magnetic field in the third direction. So sigma x3 is obviously the third component of a little vector sigma x. And I'm going to take also, so this time the lattice is going to be regular. So first actually the partition function z lambda beta h is like the integration over the phase space. So we integrate over all possible values everywhere of exponential minus beta h of sigma. And this integral means the Lebesgue integration over each sphere. And we are going to choose a specular graph, and a very regular one, and it's very important. So lambda is going to be minus L over 2 plus 1 up to L over 2 to the power d. So it's going to be a cube of size L, I mean L vertices at every side, and we label them like that, and we're always going to consider L to be an even number. It turns out that the result is just not proved for L odd, even though, of course, it's expected to be true. So, so this is lambda, and the set E is the set of nearest neighbors with periodic boundary conditions. So I don't need to explain what periodic boundary conditions are. It's quite obvious. So we declare, well, I explain it anyway. I mean, we declare that the points at the end are nearest neighbors with the other side. So here we have full translation invariance, and that's important. So the order parameter is going to be this expectation of magnetization to the square. So what we take 1 over lambda, the sum of sigma x, and take this to the square. And the expectation means 1 over the partition function, integral over all those things, all the sigma x weighted by exponential minus beta h. So this is good to expand. So this is like 1 over lambda square, obviously, sum xy in lambda, and maybe we can also sum over I equals 1 to 3, and we have a correlation, 2-point correlation function, sigma x, sigma y, in the ith direction. And I'm going to use that this is also equal to 3 over lambda, the sum over x in lambda, and sigma 0, 3, sigma x 3. So here I'm using the fact that all spin directions are the same. So instead of summing over I, you just put the 3. And translation invariance. So you can remove one of the sums over x and y and just fix 1 to be 0. And we divide by lambda. So I hope it's clear. And I'm going to call this correlation function kappa. So for some reason, this is my letter kappa. I hope it's OK. And so the point is that what we are going to prove is that when we average kappa over the whole domain, 1 over lambda, then this is strictly positive uniformly in the size of the domain. That's going to be the statement, which I'm going to give shortly. So still can write something here. So in order to state the theorem, I need more notation. And it's going to be also useful for tomorrow. So lambda star is going to denote the the lattice dual to lambda in the sense of Fourier theory. This means that concretely it's like 2 pi over L, and then we take, as before, minus L over 2 plus 1, L over 2 to the power D. And epsilon k is also going to be important. It's going to be the so-called lattice dispersion relation, and it's 2 times the sum I runs from 1 to the dimension D, 1 minus cosine ki. Okay, with this I can state the theorem, and the theorem, there is enough room here. So this is theorem 2.2 about long-range order, which was proposed by Fröhlich, Simon Spencer in 76, sorry. And it's a law bound for exactly this quantity over here, namely 1 over lambda, the sum x in lambda, this function, this correlation function kappa x, is larger or equal to 1/3 minus 1 over beta times the volume, and the sum k belongs to lambda star minus the 0, 1 over epsilon k. The epsilon k over here. And the important thing is that epsilon k is strictly positive when k is differs from 0. So this makes sense. Now what happens is that if you take lambda goes to infinity, this converges to 1 over beta as lambda goes to infinity. The integral over, well, let me write it, minus pi to pi to the d, and decay over epsilon k. And there is still 1 over 2 pi to the d, but we don't care. So the important thing is whether this converges to something finite or infinite. Epsilon k behaves like 1 over k square around 0. This is where there is potential danger. So if you're in dimensions 3 and more, the integral of 1 over k square is finite. So then you get something like finite, 1 over beta up front. So if you take beta large enough, this is going to be less than 1/3, and you get a strictly positive constant. On the other hand, if you're in 2 dimensions, for instance, this bound is not useful and does not provide spontaneous magnetization, which is actually better because Mermin-Wagner would claim that there should not be any. So this is the result. The result about this proof. And the trick is really to work in the Fourier space. And we are going to look at something, Fourier transform of kappa, and bound it using this 1 over epsilon k, and then it's a little bit Fourier theory to prove that. So let me actually give you the structure of the proof for this. So which one? I can use this one. So this is a remarkable result which we are going to, I'm just going to show you the important steps. But in the notes, which you can download quite soon, everything is given in sufficient detail that it should be readable. So the structure of the proof. The structure of the proof is as follows. So this is the theorem about the long-range order. And the first thing will be to get the so-called infrared bound. And this means that the Fourier transform of kappa is less or equals than 1 over beta with epsilon k. This is called infrared bounds. Once you have established this, it's an elementary exercise using Fourier theory. In order to get the infrared bound, you need something called Gaussian dominations, so GD, which is the property that we will introduce a certain function of fields, and this has to be bounded above by 0. So if you have such a property, it turns out that you can get the infrared bound. Now the question is how to get this upper bound over here, and this will follow from another property called reflection positivity, which is the property that when you cut your domain into two parts and you define the reflection from the left to the right, so if you have the partition function z of v, which you write as z of v1, v2, v1 on the left, v2 on the right, then this to the square is less or equals than z v1, the reflection of v1, and times z of reflection of v2, v2. And when you have reflection positivity, you can prove Gaussian domination. Let me point out that this is really nice, and I hope I will have time to explain. It's a very cute argument, which is not hard in retrospect, but a bit confusing when you do it first. So we need a little bit of notation for Fourier analysis. So given a function f in L2 of lambda, we write f hat of k to be like the sum over x in lambda exponential minus ikx f of x. And this is true for all k in the dual lattice lambda star. And then you have the inverse Fourier transform. F of x is like this. Actually, there is 1 over lambda, 1 over the volume, sum over k in lambda star, exponential plus ikx, f hat of k, and this is true for every x in lambda. Okay, this is standard, but it's always important to establish it carefully. So let me show you a little bit those steps over here as much as I can. But if you're interested, I really urge you to look at the notes for more details. The first thing is that the infrared bound implies long-range order. So let's assume that we have established something like that. By the way, kappa hat is the Fourier transform of kappa. It turns out to be a real function using lattice symmetries. It's not hard to establish. So then we assume this, and then we get then we can do the following. So 1/3 equals kappa of 0. This is not too hard to check. Kappa of 0 is the expectation of sigma 3, 0 to the square. If you just average over all spin directions, you get 1. And so this is because you get, for that reason, you get the 1/3. But then kappa of 0, we use this expression over here. And here we also distinguish the k equals 0 from the rest. So what we get is 1 over lambda kappa hat of 0 plus 1 over lambda, and then we sum over k in lambda star, but not the 0, and kappa hat of k. And then what is kappa hat of 0? Well, you have it over here. This is the sum of kappa x. So this is exactly what you want, and you have that this is equal to 1/3 minus this. And you just use the bound 1 over beta epsilon k for this, and you get the result of the theorem. Okay? So from this, you you get it automatically. So this is the first part. If you have infrared bound, you get indeed the result of the theorem, and you get a long-range order. Which one is it? The second. So second part, if the blackboard is willing, yes. We'd like to say that if you have this Gaussian domination property, then you get the infrared bound. So I need, of course, to explain what is this property. So first, let us rewrite the Hamiltonian as follows. So we can write it as minus, so no, there is no minus, sorry. The sum over nearest neighbors, and we write sigma x minus sigma y to the square. So the cross product is exactly giving what we want, and sigma x square is 1, sigma y square also. So we just subtract a constant, which turns out to be this one, and that's exactly as before. So then, the definition is this partition function with fields. So we choose real numbers at every side of a lattice, Vx. These are the V's. And given those numbers, the partition function is as follows. We integrate over the state space, d sigma, exponential, and we get minus beta sum over xy, and here we take sigma x plus vx minus sigma y minus vy. And each vx actually only acts in the third component of spin. So vx is really vx e3 for the spin directions. This to the square, sorry. So if those v's are 0, we get exactly the same as the partition function before. Maybe without the constant, but very important. The idea is to somehow probe the system with those fields which force the spins to change a bit, and to estimate the change in the free energy of the system. It's not completely easy to get really the intuition for this. It comes from field theory. But it turns out to be indeed not too hard to see the consequences. So one can state the lemma like that. Lemma 2.4, which is that assume the so-called Gaussian domination property, which is that z of v is less or equal to z of 0. For every v, we have this property. And then the conclusion is that kappa hat of k is less or equal than 1 over beta epsilon k. And this is not too hard to see, but it does require some calculation. So let me just sketch the proof. And the idea is to use the inequality, this Gaussian domination inequality, with the following field. Vx equals like eta cosine kx. So you fix k, and for fixed k, you have this real field Vx equals eta cos kx. And you're going to look at what happens for small eta. So you expand this z of v for small eta, and the case eta equals 0, you get z of 0. So you can check that there is no term linear in eta because of symmetry and everything cancels. And then there will be a term quadratic in eta. If inequality is correct here, then this quadratic term must be negative. So you get an inequality for this quadratic term. When you look at what is this quadratic term, it's some sums of cos kx, kappa of x, and so on, and you recognize the Fourier transform of the correlation function. So I'm not going to do it in the details. It does take several lines of calculations, and to get the expansion of this is not totally trivial, although it's not complicated either. Look at the notes if you don't find it easy. So then I'm not going to say more about this. That's the second step. The third step is that when you have reflection positivity, this implies Gaussian domination. And this is the step I told you is quite nice. So what is the reflection positivity? We have the lattice. And the idea is that we have this plane, this crossing, and the function R, which describes the reflection, takes one side over here and to the side across. So if this is x, this is R of x. And then you have that the domain lambda has two parts, lambda 1 and lambda 2. For those who worry about periodic boundary conditions, yes, there should be another line because of periodic boundary conditions and so on. But for the sake of the argument, does not really matter. And then the field V, we write as V1, V2. V means a Vx at every side, so we have those on the left and those on the right. And so this is in lambda 1, in lambda 2. And the lemma over here is that we assume the following property, namely that Z of V1, V2 square is less or equals than Z of V1, and you reflect V1 times Z of the reflection of V2, V2. And then the conclusion is that Z of V is less or equals than Z of 0. And the proof, so which one I can, I'm going to use the first one. So we are doing this step over here. The last step will be to prove that. Still have 5 minutes. So I'm going extremely fast. I mean, if anybody is interested, you should definitely do the homeworks and get more familiar with all those terms here. But so the proof, the idea of the proof is the following. So let V star be a maximizer. And you can fix V star 0 equals 0. The reason is that if you add a constant to the fields, it does not change the Z, because I mean obviously you are subtracting things over there. So this means that you can take a constant so that V star 0 can be assumed to be 0. And then we are going to see that 0 is also a maximizer. And so then, if V star is a maximizer, you have that V star 1 R V star 1 is also a maximizer. Why is it so? Well, just look at the inequality over here. If on the left you have a maximizer, then on the right both must be maximizers, in particular this one. And the same with V2, but we are going to use only this one. I'm also going to assume that 0 is on the left part. And then the picture is as follows. So suppose that this is 0, and you use a reflection over here. So suppose that this was a maximizer. Then you know that this is a maximizer. So this one is transferred over here. And then you get a maximizer where those two are constant. So now we have such a maximizer. We can look at this reflection over here. And then this is going to tell you indeed that when you reflect, that this and this must be also 0. I mean, there exists a maximizer with those 0. So you get a maximizer where the whole line is constant. And you use reflection over here. Did I tell you that we assume that this is true for all reflection across edges? I forgot to tell you, not only one, but certainly we assume all possible reflections. So then you use this reflection over here, and you conclude that this, you also have a maximizer where everything is constant, and then you finally conclude with a reflection over here. So this is the argument going from reflection positivity to this Gaussian domination. The last thing to get is to prove that reflection positivity holds. And I'm going to just finish. And so this reflection positivity is really the thing which is hard to prove, and that's the reason why there are all those restrictions, for instance, on the lattice having this even side length. And this is a bit long, but I'm going just to give you the idea. So you write the following. We have a z of v1, v2. And this is given by the integral over all the spins everywhere. We can distinguish the integral over spins on the left, d sigma 1, and we integrate separately with those on the right, d sigma 2. And then those interactions, we have everything on the left, everything on the right, and the terms which are coupling the left and the right. So we can write something like that, exponential minus beta, some function f, which is actually the Hamiltonian over there, sigma 1 v1, exponential minus beta f sigma 2 v2. And then we have a coupling term, which is like exponential minus beta, we sum over x in lambda 1, y in lambda 2, in such a way that xy belongs to the set of nearest neighbor edges. And we have this term sigma 1x plus v1x minus sigma 2y minus sigma minus v 2y to the square. And then there are these very clever tricks, which is that, I mean, you basically use you write this Gaussian as a Fourier transform of something, of another Gaussian, and where this quadratic terms becomes just linear. And then things is going to factorize with what happens on the left and what happens on the right, with those extra couplings. So then it will have a structure of integral over those couplings, but then you have a product of what is on the left, what is on the right. And this has the structure which allows you to use Cauchy-Schwarz, because you have some integral of a measure, a function times another function. You use Cauchy-Schwarz, and then you'll get the function and the same function, and there will be some i's which goes to minus I, and when you piece things together, you recognize exactly what you had before, but all those fields on the left have been transferred on the right, and conversely, and you get the thing over here. So since my time is up, I'm not going to give you the details. There's more details in the notes. This is really a clever argument which also takes a little while to understand, and that we are going to use also for reflection positive for the quantum system. So tomorrow we discuss the extension of Dyson-Lipsimon of those ideas to quantum Heisenberg. We go to lunch.